Good morning, everybody. Ladies and gentlemen, welcome to the second day of the 5th Smartx 2015 conference at Kafralsheikh's University. We would like to introduce our doctors. Chairman, Dr. Abdel Fattah Sion, College of Textile, NCSU, Raleigh, USA. Dr. Chatu Bedhey, Department of Textile Technology, Indian Institute of Technology, Delhi, India. Chairman, Dr. Said Nashar, Faculty of Specific Education, Kafralsheikh's University, Egypt.
Dr. Tahan, Ahmed Tahan. He's from Faculty of Applied Arts, Ready-Made Garments Department in Damiata University, Egypt. He's going to present today mathematical simulation of heat and mass transfer in primary school uniform using cotton and blended cotton polyester 50-50 fabrics. The floor is yours, Dr. Tahan.
Thank you. Good morning. In fact, I would like to welcome our guests from abroad in Egypt. So we hope to see them again in Egypt. For the moment, I'm representing the Higher Institute of Engineering and Textile Technology because I'm the dean of this institute. We'll start. First of all, I would like to thank Dr. Said Nashar to invite me here for the 5th Smartx 2015 Egypt. Also, I would like to represent my gratitude to Professor Dr. Said Higazi and Dr. Said Nashar Kai. I have done it. Sorry for that. The cooling effect of perspirations, evaporations in microclimate system on a human cottonous comfort. Would like really to discuss this event because we are really dealing with very interested or very serious part of our body, which is the next to skin garment. Human existence depends on the relationship balance between energy from body heat and the ambient transferred energy. Microclimate in the skin clothing systems, and especially the skin responses relates to the moisture and heat transfer within this system plays a critical role in skin comfort by textiles. The cooling effect of perspirations, evaporation, make use of the very large heat of vaporization of sweat. However, the skin is a large barrier organ that protects the human body from environmental hazard. The clothing systems provides an extra layers of barrier to enhance thermophysiological and sensorial comfort of the wearer. Waste heat from body, skin must be dissipated all the time and whenever necessary, aided by evaporation of sweat from the skin. Clothing has, as one of its main functions, the control of heat and moisture transfer from the body to the environment. The physical properties of the fabric's material and construction means structure and design, as well as the physical activities, the metabolic of the body, have been considered in this research by which affecting the fabric thermal properties. Skin, microclimate, and inner layers of clothing. First, the passive system is such a heat flow from the central up to the skin surface by conduction and vascular mechanism, with the skin layers preferably, which transport heat from the producing heat areas within the body to the skin surface. The heat is transferred by skin surface to the microclimate. Microclimate means the distance between the garment and the body, next to skin, what the garment with next to skin. And the garment layers associated with the exchange of heat by process of conduction, radiation, convection, and evaporation. The evaporation is very rarely interested part of this heat transfer from the body to the ambient condition. Secondly, the natural control systems which control the skin blood flow, sweating and shivering necessary heat to maintain normal body temperature for cooling. The maximum value occurs when the entire skin surface is 100% wet from regularity sweating. Both depend on the evaporative potential of the environment as a function of air movement, vapor pressure gradient from the skin surface through clothing to ambient air, and resistance of the clothing against the sweat transfer of water vapor. Let us make a comparison between human and alligator, say. Human body as a male can dissipate 1,600 to 1,800 kilocalories per day. Female is little bit, 1,300 up to 1,500 kilocalories. But alligator is 6 kilocalories per day only. Let us make a schematic diagram, the relationship between the fabric or the underwear and the skin. Suppose this is the garment, the fabric, this is skin. The skin is sweating water. I mean, just water, not evaporated. Moisture, and then these fabrics absorb this moisture, evaporated to the ambient condition, and then exchange with a fresh air, so the skin will be cool. In order to be comfortable thermophysiologically, the clothing microclimate should lie in the range of 35 plus minus 2 centigrade, 50 plus minus 10% relative humidity, 25 plus minus 5 meter per second air velocity. The fabric has its insulative ability as water and air permeability, absorbency, wickability, and other properties related to the thermal comfort. Why is that important that the core temperature remains constant? To keep vital organs warm, the enzyme systems must operate in optimum condition. The periphery of the body can withstand some deviation from the core temperature. Human temperature variation chart. So we have to understand how much our temperature is supposed to. At 30 centigrade normal body temperature, which with all the doctors measuring the temperature of a human body, start from 33. Somebody our common knows that our temperature is 37. My temperature is 36.5, different, which vary between 36 up to 37 to 0.5 centigrade. At 35, hypothermia is less than 35 centigrade, intense shivering, numbness, and bluish gray of skin, possibly of the heart irritability. You can see that in the very cold weather that your fingers is going to be bluish. At 33 centigrade, moderate to severe confusion, sleepiness, depressed, reflex, progressive loss of shivering, low heartbeat, shallow breathing, subject may be unresponsive to certain stimuli. So when your temperature coming down up to 28 centigrade in a very, very cold weather, if you're trapped in a very trapped weather, say in Europe, so you will be severe heart rhythm. In this aspect, a mathematical models has been developed to describe the dynamic heat and moisture transport of behavior. Textile material fabrics physical properties, as we used, we have measured the weight per unit area, the air permeability, the water permeability, moisture regain. Material, we have used two types of yarn were used, pure cotton, 16 by 16, the count of warp and weft, yarn and weft, twist factor 3.8 Z twist, Giza 83 Egyptian cotton. And the other one is blended cotton polyester 50-50. 4 types of fabrics were prepared on Solzer-Ruti. A set of fabrics has been made with equivalent yarn and fabric geometric. So we have to make this design to get a very near results. Equivalent yarn and fabric geometric. Full structure of the fabric consists of 16 by 150 over 40 warp 60 weft, 60 by 60, 87 by 30, 16 by 16, and so on. This is for construction we have done. While is the first structure 100% polyester weft, 150 by 2 denier, and 100% cotton with warp count of 16s. 4 fabric designs were designed to be a plain 11, 12, 22, 12, 13, satin 4 means fabric geometric is the same. The yarn through the garment swell at high humidity could have a large influence on the measured air permeability for hygroscopic fibers such as cotton, wool, represented the phenomena of TESV, the thermal effective specific volume. The relationship between the air permeability and thickness represented the thermal effective specific volume, but this relation do not show, this phenomena is very common, but for my opinion, that this relationship do not show the resistance of the fabric when the fabric contain a moisture, vapor, or sweat. So, it could be represented therefore by different way, by the air permeability and the weight of the fabric. I called it the thermal effective resistance volume. This relationship means as water accumulates through the void spaces of the yarn to yarn and the fabric by hydrophilic or hydrophilic phobic groups, there is absolutely change in the fabric thermal insulation. We can see here that the relationship between the fabric construction, and the thermal effective resistance volume, that at the very wet fabric give a very low results of the thermal effective resistance because this is very wet. 100% water inside of the fabric. When used the cotton polyester, blended cotton polyester, we can see that the wet is really behave differently. Whenever the fabric at maximum holding water, the thermal effective resistance volume rapidly increase, whereas the model 100% and 100, 50-50, the total sum of them, as I designated it, the behavior is not significant except at the satin design. So satin design really gave me a very, very interested water absorption and heat transfer. So the maximum holding water at fabric, it depends on three factors. As I designated, if we say S, the maximum holding water, A over B plus C, means A, the fabric construction parameter, B, the fabric specific weight parameter, C, the fabric specific gravity parameters, which all of them depend on the volume fraction, which volume fraction is depending on the porosity of the yarn, on the fabric also. The foregoing discussion has served to show that there are several ways in which heat and moisture can pass through fabrics in clothing environment. For example, absorption, diffusion, evaporation, condensation, and wicking of water through fiber assemblies. All have their own associated heat transport mechanism. On the other hand, the specific fibers arrangement in clothing fabrics govern the liberation of the sweat and the heat transfer from fabric in the presence of actual diffusion and water evaporation. If we can see this diagram really is representing that this is a skin, this is a microclimate, and this is a fabric, the garment, and this is an environmental condition. So the skin is wet through the microclimate region. The fabric absorbed that sweat, so started to evaporate that sweat from the skin to the ambient condition. So the four mechanism is convection, radiation, conduction, evaporation. The clothing comfort can be divided into three groups: physiological comfort, tactile comfort, thermal comfort. Physiological comfort is mainly related to the latest fashion trend and bears the attention to the properties of the fabric. The thermal comfort is the ability of fabrics to maintain the temperature of skin through transfer of heat and perspirations generated by human body. Skin sensation wear comfort, which concern the mechanical concept of the fabric with the skin: softness, breathability and movement, lack of breaking, irritation, and clinging when damp. The comfort characteristics of fabrics mainly depend on structure and design. Structure being warp and weft, and design means plain, twill, satin, types of yarn used. Then the transmission of air, heat, and water vapor from the skin through the garment are the most important factors in clothing comfort. So the heat is produced by metabolism, the very, very really interested mechanism. By other way, QM heat dissipated to the ambient due to the metabolic heat. So we are producing temperature by the metabolic heat mechanism inside our body, producing and rate of working. So this for equation to make the temperature transfer to the ambient conditions. Like evaporation, heat transfer; radiation, heat transfer; convection, conduction, heat transfer. Heat transfer by conduction is really depend on the conduction heat transfer coefficient of the used material. So we are going to now to dealing with the fabric. So we have to know, this is really a question of heat transfer of any refrigerators, whatever the equation, but this is normal in refrigerating equations. So I use these equations to be applied on the fabric. So here the factor we have to understand or have to know the conduction heat transfer coefficient of the used material. The other ambient air temperature, TS. TS here is the temperature of skin. TA is temperature of ambient condition. So skin temperature, TS, surface area, garment, the area. The heat transfer by convection, the rate of transfer by convection determined from Newton's law of cooling, which is depend on psi, the convection heat transfer coefficient of the fabric also. Actually, its value depends on garment fitting, fabric design, nature of sweat motion through the fabric structure. The heat transfer by radiation depends on the emissivity of the skin, because this is the organ which we have to deal with fabric, and so two things deal with each other: the garment next to skin and the skin. Delta is a Stephens-Boltzmann constant equal 5.7 multiplying by 8 to the power minus 8. So air does not interfere with the radiation heat transfer from the person to the ambient. Heat transfer by evaporation, this is the very most interested one, because this is one making cooling to our body. It depends on the vapor pressure between the skin surface and the microclimate. So we have to find how much the pressure difference between the microclimate of our body and the ambient condition with the garment and surrounding air. So the evaporation equation is depend on the air evaporation sweat concentration, the sweat transfer coefficient, and the air-specific heat transfer that have got value, and the pressure of the skin and the pressure of the ambient condition. So the different pressures give the mechanism to work to cool down the body. Also the TA ambient temperature and the gas constant and epsilon latent heat of the water equal 2430 kilojoule per kilogram. So we have to use this chart really to measure, to work out how much a difference, pressure difference between the ambient condition and the skin. Metabolic rates increase up to 4 or 5 times sitting resting. So the metabolism when you're doing some activities, so it will increase. So we have to know how much the skin temperature, we can measure it, but it really is not accurate enough. So we have good formula for that. So the T, the temperature of the skin is equal to this equation. We can find it in Ashery book. So skin temperature, say we have ambient temperature is 20, so the skin temperature will be 31.5. If we have got ambient temperature 31, the skin temperature will be 34.1. So you can see the change from 20 centigrade ambient to 31 ambient, 31.1 to 34.1 means 3 degrees centigrades difference, even the temperature is very high. The metabolic of 4 guys who have used is 3 children, 3 ages of children, 6 years old, 9, 12, and the metabolic of them is 8 watt per meter square centigrade, and 10 and 14 for the 12 years old. So the equation here, we have done it to represent the heat transfer of the whole things, started from the garment, skin temperature, the skin pressure and microclimate, and the garment itself, its properties, and the conduction heat transfer, the radiation heat transfer, and convection heat transfer. What we have found here, heat transfer at the fabric structure, we can find really interesting things. At wet, very wet, I mean the fabric is completely wet, at relative humidity 80%, we can find the heat transfer is very high, this one. The lowest one, the first one, the lowest, is at dry fabric at relative humidity 20. This is mathematically integrated. Effect of the fabric structure at different condition versus heat transfer cotton polyester 6 years old. We can find the same things, you know. The most interesting thing is at the fabric is very wet, I mean completely wet. At relative humidity 80% give the higher heat transfer. The lower one is dry at relative humidity 20. The contribution of blended cotton is higher than the pure cotton. In fact, this is very interesting because we know that polyester, it doesn't absorb water, but the thing is that the porosity here is very high. The combination between the polyesters and the cotton, the porosity, which really depend on how much the absorption of water through this fabric, giving a very high interesting. The high humidity prevent rapid evaporation of liquid water on the skin, give the body the sensation of heat, and eventually triggered the sweating in the first place, also causing uncomfortable feeling for the wearer. So suppose now we are, sometimes in tropical conditions, the people take off their clothes. That give them the feeling that they will be cooled down, but it's not really good. Because, now if you are setting without fabrics or garments next to skin, there will be only radiation and the convection mechanism will work. So the other two mechanisms never work. The equation of heat transfer will be only this one. Means the radiation and convection. Radiation from the body to outside, convection from the body also to ambient condition, but no conduction, no evaporation. So the very interesting really thing, if you would like to sit down or sitting without clothes, will be this diagram or this graph. Here, from 20 up to 30, the temperature is coming of the skin is coming down. So after 36 degree, the ambient condition will inject the heating of the ambient to your body. So you'll feel very warm. Effect of the structure heat versus the heating transfer, cotton fabric 6 years, we can find at wet condition the very high heat transfer. Dry one is fabric is very low. Means that the higher humidity prevent rapid evaporation of liquid water, because sometimes you will feel that when you sweat the ambient condition will cooling down. No. The evaporation mechanism will start with the ambient condition, not from your body. I mean, to evaporate something, need heat, need energy. The energy, suppose if you have got a garment next to skin, will absorb heating from your body and dissipate it outside. But if you haven't got garments next to skin, the heat energy needed to evaporate the sweat, it will be from the ambient, not your body, so you'll feel very warm. Theoretical analysis and simulation based on the physical properties measurements indicate that the fabric material contains hydrophilic phobic groups is more important. I mean, not hydrophilic only, but hydrophilic phobic, the same as a blended fabrics. Groups are more important, as well as the matrix of the structure and design. I mean, the plane wave is not better than the satin wave. The satin wave is very good because the intermeshing and the void spaces between the fibers and fiber to fiber and the yarn to fabric. The work represented here is only a limited set of conditions such as fabric material, construction, ambient condition, and the metabolic of the human body. Thank you.
We have time for one question. Any questions? If you don't have question, I have one.
Okay, sorry.
We normally, when we measure heat transfer, air breathability, comfort, we're only looking at one layer. However, we are wearing multi-layer.
Yeah.
And also when we're sitting in a chair, I feel that we still didn't do enough in this area. What's your take on how to do that?
Yes, in fact, this is for one layer. I didn't put it in two layers or multiple layers. So our mathematics really did recognize or didn't consider the multi-layers. So we can do that furthermore. The other thing is that when we are setting, this is the most represent the activity, the normal activity of the human. I mean, the 6 years old and 9 years old, 12 years old. This is really from the references, like Asheri book. So I used really all this data. They have done it in Asheri book, the very common book. So to help me in this equation to get these results.
I have one more questions. Most of the equations that you have used, they are all equilibrium equations of heat transfer. Have you used any dynamic study of temperature change as function of time?
Well, as I said in the first session, that this is a simulation. So all of it depend on what I measure. I measure the air permeability, water permeability, and doing some about the fabric construction different type of construction. So the data I started on is only the water permeability, air permeability, and the compactness of the fabric itself. So I didn't do anything more than this data. So we can the future research start on with that.
I have a comment.
Yeah, okay.
We are not asking you, actually. I was asking you to give us your take on what we should do in this research area. One of the areas that we never looked at is the environment surrounding us. Today we have an environmental room where you can control the temperature and the humidity. So you can simulate any weather,
That's right.
any outside weather. And we haven't done. We always do our research in controls, which is the standard environment, which is 65% humidity and 20 degrees Celsius.
Yeah.
However, the users are not using the clothes in such weather. Yeah, so we really need research. I'm saying, researchers have the opportunity to work in this area using environmental conditions where we can really get true data and useful data for the user.
Well,
So that's my,
yeah, that's right.
Non-researcher.
You're right. Yes, you're right. In fact, here through this research, I put my simulation at relative humidity 20 up to 80, and I estimated through this equation about 25 parameters to know what the effect of the humidity over. And also, I used this chart to know the pressure difference between the ambient condition and the temperature of skin and this equation of skin temperature. So the whole thing is as a refrigerations or cooling down the body is using as laws of refrigeration. So, well, in the future, I can consider some of yours. You are
I
correct.
understand what you did in simulation, but talking about verifying experimentally.
That's right.
We need to do it.
Okay.
All right.
Thank you.
Thank you very much.
Next speaker is Professor Kushal Singh from India.
Professor Kushal Singh is with Indian Institute of Technology, Delhi. He is our colleague, and presently he is the Dean Faculty in the Institute. He is basically a textile chemist. At the same time, he is working nowadays in this area of organization to develop conducting textile yarns and fabrics.
Can I say something? He is very good singer also.
Good morning to all of you. I am really thankful to Dr. Syed Al-Nasha for inviting to this conference, Smartx. The way the name goes, that it makes everybody smart. At the end of the conference, people will become smarter, not necessarily by dressing up, but probably by becoming wiser, by learning more about things that are happening, and hopefully things will be good. This is my first visit to Egypt, so therefore I was excited otherwise also to come here and see the country, see the people. So far so good. I have loved the places that I have visited. I have loved the people we have met. So I'm sure the next few days are also going to be beautiful, and I hope to enjoy them. Dr. Tahan has made you comfortable. Are you comfortable now? Because he's talking about comfort all the time. Fortunately, we're not perspiring because you're in an air-conditioned environment, so your comfort level was high. Shall I make you a little more uncomfortable? Yes. So, how many of, I understand some people here are from chemical engineering. How many of you love chemistry? All right. So, the large number of people don't seem to be in love with chemistry. It so happens all the people who generally join even engineering education, when you ask that what have you studied, physics, chemistry, mathematics in school, and you come to engineering college and want to say which is the subject you like the most, invariably they may say physics or mathematics. When you talk about chemistry, they will say, well, no, I don't like chemistry so much, but anyway, I had to do it. Could not do much about it. What I normally say is the chemistry is a mystery till you have understood. So once you understand, it's a very logical kind of situation. But let me not scare you, I'm not going to be talking about chemistry, although the problem that I'm talking does relate to some kind of chemistry. This is chemical, electrochemical polymerization. So when you talk about polymerization, therefore some chemistry has to come in. But we will leave the chemistry part out of it. Only some of the results that we have seen, maybe I'll share with you. Hopefully, this will be interesting to you. You see, when we talk about textiles, polymers, and whatever, these materials are insulators, you know. When you pass electric current to them, they don't conduct electricity. So when we want to make sure that they somehow conduct electricity, so we know there's a copper wire running all around in this building, light is coming, so copper, metal, aluminum, all are conducting materials. So textile people also sometimes become smarter, like Smartx is a conference, so you become smarter. You start adding metal wires, threads into the textiles and you can make them conducting. Sometimes the carpets that you have here can be having underline, lining, a little bit of wiring, so that if the carpet, for example, is a synthetic carpet, you can develop a lot of static charge. You can actually see sparks. In winters, any one of you have removed, do you wear other than cotton, because Egypt is known for cotton, do you wear polyesters and nylons? Do you wear polyesters and nylons? Yeah. Sometimes when in winter you take them off, do you feel something, some spark somewhere? Sometimes when you get out of your car, do you see some spark, some shock? Have you experienced? Yes. Right, so if the carpet is lying like this and it's a nylon carpet, for example, and people move for about 15-20 minutes or half an hour, 1 hour, you can speak good amount of sparks. And therefore, conductivity becomes important in textiles also, that you must dissipate. So this is one way you can make things conducting by putting metal, because we know metals conduct electricity. Another interesting thing which has come, you see this chart, which is a bar. Normal, let's say nylon, is very resistive, very, very non-conducting. It is at the bottom of the scale. The copper is at the top of the scale. But in the recent years, people have found that polymers, which are like nylon is a polymer, polyester is a polymer, they can also conduct electricity. So they are called conducting polymers. So this is not thermal conductivity, but electrical conductivity. So if you want to make textiles conducting electrically without using metals, you can use metals and make it conducting, and if you don't want to use metals and make it conducting, there is some possibilities. Why do you want to use textile? Because textile as a material is one of the best materials. This is a material which is flexible. How many times have you washed your dresses? 100 times maybe. and they still look like the same. Can you think of washing a ceramic pot in a washing machine and actually get out the pot? You'll get pieces. So it's beautiful material, flexible material, and therefore it is durable also. If you can make textiles conducting without using metals, maybe they will become more durable, more flexible, and so on and so forth. How can we do that? There is a polymer or a series of polymers types which are called inherently conducting polymers, which are called ICP, inherently conducting polymers. A person called Dr. Heger got a Nobel Prize. He was a man from physics, got a Nobel Prize in chemistry because he could find some materials which can conduct electricity. It has opened a new era of material science, completely new era of material science, where polymeric materials can conduct electricity. You may not use metals at all. You may have flexible electronics, you may have flexible sensors, and everything could be very, very flexible. And therefore, this is a very exciting area, very exciting area. A lot of people are working in this area these days. Some of these materials which he initially represented, people have tested it all. Started with polyacetylene, polyaniline, polypropylene, polypyrrole, polythiophene. You see, people who are young, they use umbrellas. You use umbrellas? Right? They are very colorful. Not so common, it doesn't rain so much here, but still. Right. But the people who are little of my age, they've been using umbrella, which always used to be a black color. You know, the big umbrellas, the black color umbrellas. They were being dyed with what we call as polyaniline. Polyaniline was being used to dye them. But that time people did not know that this polyaniline could actually conduct electricity also. They were only using to make a black colored fabric, which was very fast to light, very fast to washing, very fast to things, so very nice color. And this person found that in case you can make a chemistry like this, which I am not going to discuss, where have conjugation. Conjugation means how many people actually read chemistry, other than those 5-7 hands. One is you love chemistry, others you have read chemistry. In any case, there is something called single bond, double bond kind of a thing. If these bonds are conjugated, that is one after the other, one single bond followed by one double bond and a series of polymer things, then electricity can be conducted. This is what they found. We in our group have worked on many such polymers, which is one of them is polyaniline, polypyrrole, and polythiophene. I'm going to be discussing partly some of those things. Now, I want to make textiles conducting. So if you have inherently conducting material, you can make conducting polymer, you can try to make films or fibers. It is very difficult, very, very difficult with these type of polymers. They do not easily melt, they do not easily dissolve. So making fibers or film is quite difficult. One can take these polymers, make them powders and mix them in polymer blends and then make something out of it, which is melt blending or solution blending. That's also possible, but somehow limitation is there in these areas also. One of the other approach which we believe can show the way a little bit, the textile and these polymers together, is what we call as in situ polymerization. In situ means wherever it is, on the job, on the fabric itself, the polymerization takes place, not somewhere else. One of the ways of polymerizing is chemical polymerization. Other is electrochemical. Are you becoming uncomfortable now? Chemical, unchemical, so it doesn't matter. It's all right. Electrochemical polymerization. So, I'm not going to be talking about the polymerization, but some of the part of some study which one of our students did, I'm going to be talking about. So I did say that we worked on pyrroles, we worked on thiophenes, but there was a property differences. Polypyrroles are very good conductors comparatively. Thiophenes are less conductive, but they're very stable. The stability also is important. So we thought we'll try and mix them up and see what we can do and study the electrical resistivity, effect on polymerization, morphology, and maybe thermal stability. These are some of the things which we thought we will try to look at the mixture. So let's not worry about it. This is where the chemical polymerization were done. What I have marked is, in the circle, is a solvent. You normally have to use some solvent to do the job. We had tried water, we tried acetone, we tried alcohols, not for drinking, but for this purpose. But we found that with mixtures, acetonitrile is one solvent which gives better results. So we worked for this also. Electrochemical polymerization is where you do not do anything, but you pass current through solutions, and therefore deposition takes place. Here also we had to do a bit of an exercise, and we found that other than the solvent which is called acetonitrile, the electrodes that are there, we could use metal electrodes, steel electrodes, but we found a carbon electrode is the one which works better. Another chemical also we had to change, boron trifluoride ethyl ether. Some characterization which we did, which is called surface resistivity. You can measure how the current flows on the surface of the material like a textile. And to see the micrograph, select scanning electron microscopy or EDX and thermogravimetry. These are some of the tests which we did. So just to check out, we changed the, looks like some material has been translated into Egypt. I can't read it, you can read it? Right, the letters have gone. No problem. So the word, whatever was in the word format has got into Egyptian format. It's all right, no? I can't understand, at least you can. What is happening is from one side to the other side, the ratio of the two monomers has been changed. One 100% pyrrole, on the other side it is 100% thiophene. Those type of things. And we saw that the resistivity increases. It's quite conducting material, by the way. When you have 4 kilo ohms kind of environment, it's quite conducting. But one can make it more conducting also. But that was interesting. Similar experiment which we did, an electrochemical polymerization in a cell, which we call a polymerization cell. We saw the same thing, that the polymerization, the resistivity increases. That is, pyrrole, if it is less, then the resistivity keeps changing and it increases. If pyrrole is more, the resistivity is less. That means more conducting material can be produced. Then we measured the material obtained, the material in grams, how much polymer was actually produced, deposited. That also is very clearly, it decreases as the thiophene component increases. So we wanted to understand as to why this happens. There's one test which I said is called the EDX or electron dispersion X-ray technique, which can tell which type of elements are on the surface, whether it is nitrogen or sulfur or whichever metal that we talk about. It can talk about, it's like an electron microscope with another, you can say a sensor which can detect the electrons coming out of the after interaction, which can text which type of elements are available. So what was interesting, which is here, if you can probably try and see, that when we change the percentage, here it is all right written, as the percentage changes, the thiophene has sulfur, while the pyrrole has nitrogen. So if you measure how much nitrogen is there and how much sulfur is there, we can say the ratio of these materials on the surfaces. So one found that theoretically, obviously the ratio was changing from one value to another, higher value to the lower value. But when you do actual measurement, the values were higher. The nitrogen was higher, which it means that pyrrole is, despite being low, is going more onto the surface, getting more polymerized. And therefore, one could find that despite everything else, despite the fact that the content of pyrrole is less, in the polymerization, after the polymerization, the pyrrole actually was more, polymer was more. But we can, this is something not so important. And we found that the nitrogen that you have in pyrrole versus the sulfur that you have in thiophene, the electronegativity, if it is not so very uncomfortable, this is a term which people use to see how electron transfer takes place, how the reaction takes place. Somewhere the reaction must take place. So pyrrole out of them is much more reactive compared to a thiophene. In electrochemical polymerization, current flows from one electrode to the other through the solution, and on one side polymerization takes place and some gases evolve. But the important thing is, if you can measure the variation in current, even if you keep the voltage constant, the current actually flowing through the system changes. You've seen physics, at least, if the chemistry is not right. The current changes, and the current is, in every case, is a different thing. Higher is the possibility of passing the current, higher is the energy transfer, and therefore higher is the polymerization. And this relationship we had established earlier. And you can see, depending upon which type of composition we are trying, the current with time is actually changing. And so thiophene has the lowest, thiophene has the lowest at the bottom current, and therefore gives less polymerization. So we understood as to why it gives less polymerization. Also, when we studied the surface of materials, you can see if the thiophene is less and pyrrole is more, you have very globular kind of polymerization which takes place, which is on the other side, while when the thiophene is more, you take more planar type of a surface. This is how the films get formed. So the difference is there in these two materials. Also, we did a thermogravimetric analysis for the people who understand this, is that you heat the material for different temperatures and see how the weight goes down. At some stage, the weight will become zero. All the carbon, nitrogen, everything will get evaporated. The test was done up to 700 degrees centigrade. 700 degrees centigrade, no fiber actually can be seen. But these films, these tests were done, for example, on some films, and these films still stay up to 500, 600 degrees centigrade. You can actually see them. But it shows that thiophene is a stronger one, it's more stable. Pyrrole, polypyrrole is less stable, but together they help each other and they become slightly better, in between the stability it comes. Some of the conclusions that we've drawn from this small study is that electrochemical polymerization with mixtures of pyrrole and thiophene is feasible. You can make them and the conductivity can be measured. Quite low resistivity could be obtained, which means more conducting material could be formed. Rate of polymerization of pyrrole far exceeds that of thiophene. The morphology of polypyrrole is more globular, and presence of polythiophene enhances thermal stability. I'm not sure whether the audio is connected, but I don't know, maybe I can use this mic to see if the audio is seen. Let's just see. You've seen some of those uncomfortable movements with me, something which were not very helpful maybe. Let me see if this one helps you and if you can hear the audio. Sorry. I don't know from where the audio is coming. you can't see the audio from anywhere. So let me just go back and tell you what exactly is happening. This is the test material being done. I'll just keep stopping it in between. This film is based on the applications, possible applications of an electrically conducting textile material, possible applications. One of the application is called EMI shielding, electromagnetic interference. For example, if you're speaking here and your phone rings here, you will see noise coming there also. And so the electromagnetic radiations interfere. So in electronic systems, sometimes you like not to be interfered, or sometimes because of radiations you can find out something which is existing or does not exist. So I'll explain what exactly is happening. So this is about EMI shielding. This person is trying to call the other guy, all right? You can't hear it because there is no audio here. So he is able to hear the phone because both the people are able to now communicate. So they can hear each other. But when this fellow puts this material, this phone inside this pouch, okay, and now this fellow is trying to call and the message is coming, the phone is not reachable or is it switched off, all right? That means very near each other, this material, which is a textile material without any metals, can do interference shielding. So it can work without anything. When you take it out, it can hear. So tomorrow, suppose you have a defense analysis systems, you put an electroconducting material or on the top of a material like a tank, people may not be able to find. Another is this material which can be used as heating system. If you pass current, when you have a heater, you've seen the room heaters, you pass current, the heat comes out. Here it is only textile. It can also get heated when you pass current. In a 6-volt battery, this particular thing can actually give you temperatures from almost 26 degrees to 40 degrees as the temperature rises in less than around 2 minutes or so. And so the temperatures can go up to 35, 40 degrees. So if you can make pads, in winter, for example, you have a blanket or something, these type of materials can be used where there is no metal out there, but it can still heat. A 5-degree rise is a very good rise, and for comfort purposes, if you have a jacket or you are doing mountaineering, it can be very comfortable if 5-degree change can be brought in by just simple battery that you are carrying in a pocket. This is an experiment. The black thing that you see is a polyester fabric which has been treated by this polymerization process, and it has enough conductivity that you can see the light, which is a CFL bulb which can be lighted, and the current passes through this. You can see this? Then it can be used an electronic system also. This boy is actually touching something which he had drawn on a textile material from a conducting polymer, and if you can probably see the light, the LED actually gets lit. Can you see that LED lighting? So just by touching, so there's enough small little current passes. This material is like a strand of fiber where the arrow is there, just a yarn which is conducting like this. It can act like a gas sensor. So this girl now is kept this in this desiccator. Is trying to pass ammonia gas. When the ammonia gas passes through this material, as is going through this and coming to that particular point, the resistance changes quite a lot of this circuit. And if you do the reverse thing and pass the air, resistance goes down. What it therefore means is you can actually have gas sensing systems also developed by these type of materials, which are different kind of applications. One, whenever there is a conducting happening, you have electromagnetic effects. This is a small experiment. You can watch that small little thing hanging in that. When the power gets switched on, it vibrates or it does a bit of a action. So if you see the lights, whenever the lights switch on, there will be some little vibration taking place. You see that? It's an electromagnetic effect. And then, we don't know. Are you using these kind of devices which are called capacitive touch mobile phones? So every time you use it, but in winter if some people use gloves, it does not work. But if you use a bit of a conducting material, which we call as the gloves of the Midas touch, this will start working. So your conducting material can help in many ways. And there are other various applications which can be used as compressive gauges, strain gauges, those type of things also in a flexible system can be made use of using flexible non-metallic textiles, electroconducting textile. So this is some of the examples which I thought I just want to view. It would have been probably better maybe if the voice was also coming, but my voice was okay. Now, that's the only thing I have to say. Thank you very much.
So, is there any questions? Any clarification?
How much current could be through these fabrics? I mean, 7 volt, 9 volt, 100, 120, but how much?
All right, good question. Did you, when you saw that fabric lighting the CFL bulb, so that's the current which required. You can't light a CFL bulb with a 6 volt, 9 volt battery. So it was actually 220 volts being connected to that fabric, 220 volts. In India, we follow a 220 plus or minus 20, that kind of a voltage we say. And the electronic circuit that you see, very small current, just touch by hand and the current passes. Just a touch of hand and the current passes. Well, thank you very much. Hope you enjoyed whatever you enjoyed, the chemistry. All the best.
Hello. I'm here today to give information about the study of our work team, rheological evaluation of textile fiber extended engineered composite materials. Engineered composite materials, including textile fibers, in their structure are amongst the imported industrial materials. What different it is, textile fiber, extended composite materials from classical composites, is processing and performance that can be achieved with the manipulation of included textile fibers and their parameters. The main advantages of composite materials are many materials may be selected, economic, aesthetic, being lighter in weight, eco-friendly, performance-oriented, as well as suited for diverse applications. One way of achieving some of the above functionalities is by using textile fiber materials as a filler material in different polymer blends. With the addition of textile fiber, we can increase strength, adjustable stiffness, and reduce weight. Majority of engineered composite materials consist of thermoset epoxy matrix reinforced with continuous various type of fiber. Epoxy is a versatile and widely accepted matrix material for fabrication of the advanced composites because of its excellent bonding, thermal, mechanical, dielectric, and aging characteristics. Thermoset epoxy resins are widely used as coatings, adhesives, molding compounds, and polymer composites because of their superior thermomechanical properties and excellent processability. However, the use of thermoset materials is often limited because of their low toughness property. Therefore, the bulk amounts of epoxies are usually blended with toughners used as the second phase in the composites resin system. However, the toughners always affect the processability of the system. Because of the flexibility present in the structure of epoxy, it could be used as one of the blend components in this study. The parameters of textile fibers are physical properties like denier, length of fiber, and crimps, design like chrome or base fabric, mechanical properties like tensile strength and elongation, inspection and repair, and tooling. These materials can be changed easily and greatly. You can see image below some based fabric design. The primary goal of this research was to determine the effect of load on rheological properties of the textile fiber extended composites. The main focus of the work was to investigate the compatibility effect of miscible epoxy ultra-high molecular weight polyethylene fiber blends on rheological and mechanical properties of the final composite material. For this purpose, a blend of epoxy ultra-high molecular weight polyethylene fiber composites were prepared as a function of ultra-high molecular weight polyethylene fiber in different weight ratios such as 0%, 0.5%, 1%, 1.5%, 2%, 2.5%, and 3%. The final objective of this study is to optimize a suitable textile fiber extended polymer composite which offers low cost, high strength material, which can be applied in making lightweight components for various parts, systems, and consumer products. In this study, the resin used was epoxy Siba Geigy araldite LY 556 and amine hardener HY 951 with 10 units hardener to 100 units resin. In addition, ultra-high molecular weight polyethylene fiber type TM30 brand Doyan Trontex China was used as the filler material. Firstly, fiber was chopped in a definite shape. Then, weighted amount of these fibers and epoxy were mixed thoroughly with mechanical stirrer for about 30 minutes at ambient temperature conditions. Once the process was completed, hardener was added to the epoxy mixture. A silicone mold with recurred dimensions was used for making samples with ASTM standards. To ensure complete curing, the blended textile fiber extended composite samples were post-cured at 70 centigrade for 90 minutes, and the test specimens were obtained. Tensile testing samples were prepared in dumbbell shapes with dimensions as per ASTM D638 standards. In each case, 5 samples were tested and the average value was tabulated. A 3-point banding test was carried out to determine the interlaminar shear strength of the samples as per ASTM D2344. The testing was performed on beams of 15 mm times 100 mm times 5 mm at crosshead speed of 1 millimeter per minute, mentioning the sample size of 5 for each experiment, and the average value was tabulated. Tensile strength and interlaminar shear strength tests were carried out using Hansfeld universal testing machines. The primary goal of the blended composite materials as a product is to observe the resistance to applied mechanical forces. It is achieved by load transfer between the matrix and the fibers induced by the shear deformation of the matrix around the fibers. This shear deformation is produced because of the high elastic modulus of the fibers and the larger differences between the mechanical properties of the composite constituents. Table below shows effects of the epoxy ultra-high molecular weight polyethylene fiber composites as a function of the fiber content. It was observed that mechanical properties were optimized at 2% fiber content. When compared with neat blend samples, 2% fiber-filled blend samples gave the following results. Tensile strength showed a 57.8% increase, while the interlaminar shear strength showed a 63.7% increase. Compared to the neat blends of the epoxy blends, with the addition, fiber exhibited remarkable improvement in the mechanical properties. In this study, the mechanical properties of epoxy resin reinforced with ultra-high molecular weight polyethylene textile fiber were studied. It was observed that mechanical properties were optimized at 2% fiber content under the experimental conditions studied in this work. When compared with neat blend samples, 2% textile fiber blend sample gave the result that tensile strength exhibited a 57.8% increase, while interlaminar shear strength exhibited a 63.7% increase in strength. This ultra-high molecular weight polyethylene fiber extended composite can be applied in making lightweight components as parts to be used in automobile and transportation systems and consumer products. Thank you for listening.
I invite the next speaker, Mr. Arvind Sonmez. He is going to speak on technical textile production.
We prepared this presentation with my friend, Mr. Abdullah. There is a big gap in the field of technical textile in Egypt. This presentation for businessmen, because they can invest, and for students, and for academic personnel. There is no one target. Especially dear student. Yesterday, Professor Mohammed talked from National Research, and the before speaker, if you want to work in the field of technical textile, I think you want, because these products are expensive and your income will be more, but in the same time difficult. You have to follow the chemical faculty and maybe physics.